All right, welcome back, everyone. So, after 8 labs of building this robot piece by piece, we are finally here. This is the capstone, the grand finale. This is where all that groundwork we did really starts to pay off, because today, we're building a robot that doesn't just follow lines of code, it actually understands a command. Okay, let's get right into it.
At its core, this whole project is about a fundamental shift in how we think about robotics. We're making a leap from the old way, hand-coding every single little movement, to something entirely new. We're on the vision, language, action journey. And that's all about learned autonomy, creating a system that can genuinely learn a task just by watching an expert do it. And this is what it all leads to. The incredible results of that big shift. You just type in a simple command, something like pick up the red cup, and the Unitree G1 robot, right there in our MuJoCo simulation, it just does it. It sees the world, it understands what you asked for, and it carries out the task, just like that. This is the magic we're going to unpack today.
So the big question is, how does this magic actually work? Well, it's not really magic. It's all thanks to a really powerful architecture, the VLA, or Vision Language Action Model. So let's go ahead and peel back the layers and take a look at the blueprint for this amazing system.
Okay, so here's the entire journey that information takes. It all kicks off with a language command, which gets processed by a model called CLIP. At the exact same time, the robot's cameras are feeding it vision data. Then you mix in proprioception, which is just a fancy word for the robot's own sense of where its joints are. All of this info flows into the main policy, which then predicts what to do next. Those actions get smoothed out, and finally, they're sent to the simulator to make the robot move. And get this whole symphony of data happens more than 10 times every single second.
And this really brings us to the core idea of this whole project. Think about it like this. In all the previous labs, we built what you could call an analytical brain. It was a complex system of hand-coded controllers that defined every single step. But now, we're swapping all of that out for a single learned brain, a neural network that figures out what to do just by watching an expert. And this is so much more than a cool trick. It's about making robotics way more flexible. Instead of spending weeks writing code for a new task, you can just show the robot what you want it to do. Of course, for any system to learn anything, it's got to have a good teacher, right? So the very first and maybe most critical step is creating a ton of high-quality demonstration data. This is basically the textbook that our robot is going to study from. Now, this is where things get really clever. Instead of having a person sit there with a joystick trying to manually guide the robot, which is super slow and full of mistakes, the team used the perfect programmatic controller from Lab 8 as the expert. This means every single demonstration is flawless. It's fast, it's consistent, it's repeatable. It's literally like having the world's best, most perfect teacher on call 24/7. But a good teacher doesn't just show you the exact same problem over and over. To make the robot's policy really robust, they use something called domain randomization. So every time the expert did a task, the scene was slightly different. The cup was moved a bit, the lighting changed, the colors were tweaked. This is so important because it teaches the robot what really matters for picking up a cup and what's just, visual noise it can ignore. And we are not talking about a small effort here. To build a dataset that's actually reliable, the team collected over 250 complete successful demonstrations. That's across 5 different tasks. That is a massive amount of high-quality data, and it's the foundation for everything that makes this robot smart. Okay, so we've got the data, we have our textbook. Now it's time to actually train the robot's brain. And that brain is called the ACT policy. It's the neural network that takes in all that sensory info and decides how the robot should move. So a really crucial idea behind the ACT policy is this thing called action chunking. See, instead of thinking just one tiny step at a time, the model predicts a whole sequence, or a chunk, of 10 future actions all at once. And this is huge. It lets the robot make these smooth, committed movements, and it prevents that jerky, hesitant motion you so often see in robotics. But for the policy to make any good decisions, it needs good information to begin with. So how does it actually see the world and understand what we're telling it to do? Well, it all comes down to 2 key inputs, vision and language. On the vision side of things, you can think of the robot as having 2 eyes. There's one camera on its head, which gives it this broad, contextual view of the whole scene. And then there's a second camera on its wrist for that close-up, detailed view when it's manipulating objects.
Images from both of these cameras get fed into these powerful resonant models, which basically boil down all those pixels into a compact, meaningful idea of what the world looks like. And then for the language part, the system uses a pre-trained model called CLIP. This thing is an absolute powerhouse that you can just grab off the shelf. It already has this deep understanding of text. So it takes our command, pick up the red cup, and turns it into a string of numbers, a vector, that the policy can immediately understand without having to be trained on language from scratch. And this right here is where it all comes together, the CVAE transformer. This is the heart of the whole policy. It's a really sophisticated piece of architecture that takes the processed vision, the processed language, and the robot's own joint positions, and it fuses all of that information together to predict that next chunk of 10 actions. Okay, so the brain is trained. Now, it's the moment of truth. Let's put it to work. How does this system actually run in real time to generate that smooth, intelligent behavior we're looking for? So this is the real-time loop that's just happening over and over and over again, incredibly fast. The simulator renders new camera images. Those images and the language command get encoded. The policy spits out the next action chunk. A special blending technique gets applied to smooth things out, and finally, that smooth action is sent to the robot's motors. And this entire cycle has to happen in less than 1/10 of a second. It's amazing. Now, one of the secrets to the robot's super smooth motion is a really clever trick called the temporal ensemble. Since the policy is predicting a new chunk of 10 actions every single step, you have all these overlapping predictions. This technique just blends them all together, giving a little more weight to the newest predictions. And that's what prevents any sudden, jerky movements and keeps things looking fluid. And here's a fantastic little bit of practical engineering. The model is trained using full 32-bit precision for maximum accuracy, right? But for actually running the thing, it gets crunched down, or quantized, to 8-bit integers. This makes it way faster and lighter, letting it run at over 10 frames per second on a normal computer. And the best part? It still maintains over 90% of the original success rate. It's truly the best of both worlds. So as we start to wrap this up, it's really crucial to see this lab for what it is. It's not just some standalone project. It is the true culmination of this entire 9-part journey. It's the point where everything we've built finally comes together in a new and incredibly powerful way. And here's the key takeaway. This learned policy could only exist because of all those analytical controllers we built before it. The impedance control from Lab 3, the grasping logic from Lab 5, the walking from Lab 7, all of that came together to form the perfect expert that served as the teacher. In a very real sense, the learned brain learned everything it knows from the analytical brain. And this wasn't just about making a cool demo. No, this was an engineering project with a clear, measurable goal. The target was to hit a success rate of over 70% on this final capstone task, and to do it over 10 consecutive trials. That really holds the project to a high standard of reliability and performance. And so this is where we end up. We've managed to replace a massive, complex, hand-coded system with a single, flexible, learned policy. That is a monumental leap forward, not just because it simplifies development, but because it opens the door to robots that can actually adapt and learn new things. And it leaves us with one final, very exciting question to think about. Now that the robot can learn, what should we teach it next?